Hey everybody, welcome to chapter 9. We're talking about correlation, which you can literally think of as the two words co-relation. So we're going to talk about how do two different variables relate to each other. So first, as a reminder, we're going back to all the way to chapter 1, where we were talking about the difference between correlational study designs and experimental study designs. And so today we're mostly talking about correlational data or correlational study designs. And of course, correlation does not necessarily imply causation. Here's a funny tongue-in-cheek kind of cartoon that illustrates this. Every single person who confuses correlation and causation ends up dying, which is true, but not because of the fact that you confuse correlation and causation. It's because, well, at some point everybody dies, right? So that while this statement is true, it is not a causal statement in that confusing correlation and causation actually kills somebody, right? So in correlational studies, we don't assign people to different conditions or the same people to different conditions in experimental groups or control groups. We don't do any of this experimental manipulation. Basically, all we do is we either take people into the lab or we give them a survey online. They fill out a bunch of different measures. We didn't manipulate anything. We didn't assign them to do any type of experiment. And then afterwards, we just see, well, what are the natural relationships between the variables that they filled out? And what do I mean by relationship? I mean, well, when somebody scores really highly on a variable, or you see that the variable people are scoring, in a number of different ways, but as one variable tends to increase, what happens with the other variable? For example, in students, how strongly related, in other words, what is the relationship between the number of hours spent studying for a final exam and the final exam score? So you could say, okay, well, a student who studies a ton of hours, what do we see happen with their final exam score? Is it going to be low? Is it going to be in the middle? Is it going to be high? And if you see enough that many people who study a lot also do really well on the exam, then those two variables are probably related, positively related, and we'll talk about that in a second. But when we use correlational data, we have to be really cautious about the conclusions we make from these data. Because you'll remember in experimental designs, we're randomly assigning participants to different conditions. Therefore, they're kind of canceling each other's out in terms of like other variables that might affect the outcome, even though we don't want them to. So that's a way to control for factors outside of the things that we're purposely studying. But in correlational studies, we're not randomly assigning people to anything. We're not actually controlling their environments in any really specific way. And so we can't actually say that, oh, well, I've controlled for all the other factors. So the only thing that could affect the outcome variable, the dependent variable, is whatever I've changed, the independent variable. But in correlational studies, we don't control for a lot of other factors, at least with using research design methods. And so since we can't control for all possible variables that might influence the outcome, we can't say that for certain whatever variable we're interested in, the independent variable, actually causes a change in the dependent variable. So in correlational studies, we don't say that an increase in one variable causes an increase in the other variable. We just look for relationships between two variables. Your book says both of them are dependent variables for some reason. We don't really talk about like dependent variables and independent variables as much in correlational studies because you're just looking at how are two things related, and the actual in like the real world, the capital T truth of the relationship between those two variables meaning does one thing cause the other? Does the second variable cause the first variable? Is there a hidden third variable that actually causes both of those things to change? You don't actually know from correlational studies. So we don't talk about causation. We don't really talk about direction of effects or something like that, because it could be the case that, let's say, studying more actually does lead to better final grades. It could also mean that better final grades actually leads to more studying. And you say, well, how does that work? Well, maybe because you are excited that you did well on a previous exam, maybe that means that you'll study harder for the next exam or something. Or maybe there's a separate factor, like a personality trait, that causes people to be more studious and do better on exams, right? So we don't actually know. Now, the pros about correlational studies is you can just test natural relationships amongst variables in the real world. Like, we can take people in and ask them how anxious they are in general, and also ask them about their exam scores, and then just see, like, well, do people with higher anxiety tend to do better or worse on exams? Versus in an experimental method, you'd actually have to find people who you'd have to manipulate anxiety and actually make one group of people anxious and have another group of people who are not anxious, and then you'd compare means of exam scores. So it's a different situation though, because you're kind of falsely putting people into a certain mental state, right? The problem is, obviously, again, we don't randomly assign to conditions, so there's a lack of control, and we can't assume causality of variables. Here's a funny little social media post that's saying, as you can see, the rise in profanity on Taylor Swift albums on the left is having an unusual effect of causing a dramatic rise in the installed solar power capacity of the United States. And this is obviously, those two things are obviously not related, or maybe not so obviously not related, but we can't assume that because Taylor Swift is cursing more on her albums, even though we see a concordant increase in solar power capacity, it doesn't mean that these things are causing one another, right? Your book offers a pretty good example of this, I think. It says that imagine there's a study that shows a link between coffee and cancer. And you have to think about this word link or association or things like that. And I'll talk about that more in a bit. But if we say, oh, maybe there's a link between drinking coffee and cancer, then you could be really tempted to conclude that drinking coffee causes cancer. But that's not necessarily true. In correlational studies, there could be multiple directions of effects, or even a completely opposite or different effect than what we actually think is going on. So the possibilities, if you see that, oh, well, it looks like people who drink a lot of coffee also tend to develop cancers a lot. Well, you could also say that, well, the people who have cancer frequent, or like develop cancer at a high rate, maybe they drink more coffee, right? So it's possible that people who are drinking coffee, maybe that causes cancer. That's one possible direction of effects. The other possible direction would be that no, like people who have cancer drink a lot of coffee because it helps ease some kind of anxiety or symptoms around that. But maybe there's a third or fourth or fifth or sixth explanation, which is other variables influencing both of these factors at the same time. And so your book says, well, what about people who are just naturally more anxious? And so high anxiety might cause people to both drink more coffee and develop more kinds of cancer. And so there could be a hidden third variable that wasn't even originally measured that could be increasing both cancer and coffee drinking at the same time. And this is called the hidden third variable problem. In correlational studies, we just don't know because we haven't controlled for other kinds of things. We just can't be sure that there's not a third or even several other hidden factors that we didn't measure that are actually kind of pulling the strings, so to speak, and affecting both of these variables. So in all the previous statistical tests we've talked about so far this semester, we've been talking about comparing means. And that means you have, either different samples in terms of like an independent t-test, or you have the same people to go through two different conditions, as in, a paired subjects t-test, or you're just comparing one sample mean to a previously established population mean, like, in one sample z-test, one sample t-test. Or ANOVA, you're going to be comparing multiple different conditions or situations in terms of their means. So those are all because you have different samples or different conditions, okay? But that's not really what we're interested in when we're talking about correlation or, in fact, regression. We're talking about relationships between variables, not necessarily just the means between variables. And this graphic or this chart is showing you that, well, it also depends on what type of variable, what scale of measurement your outcome variable or both of your variables are on. If you've got two variables that are on a ratio or interval scale, and you're interested in just describing the relationship between them, then you're going to do a correlation using what's called a Pearson R-test. If you want to have one variable and predict another variable from that variable, then you're going to use a regression test. We'll talk about both of those today. If one of your variables was on a nominal or ordinal scale, just kind of categorical scales, then we'd use a chi-square test, but we're not going to talk about that in this class. So when you're interested in describing the correlation or the relation between two variables, you're going to use a Pearson R-test. So before we've used t-test, we've used ANOVA, which is f-test, we've used z-test. Now we're going to use a Pearson R-test, and it's still a significance test like all the other ones, meaning it's going to give you a p-value and you compare that to 0.05. But this is for a linear relationship between two variables that are measured on interval or ratio scales. The interesting thing about this is, because it's a specific ratio, which we'll talk about in a second, the lowest value possible for a correlation is -1, and the highest value possible for a correlation is 1.0, +1. And the negative and positive indicate the direction of the relationship, whereas the actual number itself speak to the magnitude or the strength of the relationship. Let's talk more about that. So if you end up with an R value that's really close to -1, or an R value that's really close to +1, those are super strong relationships. -1, -1.0 is the strongest negative relationship. +1.0 is the strongest possible positive relationship. So negative R values, negative relationships, mean that as one variable tends to increase, the other one tends to decrease, versus positive R values mean that as one variable increases, the other one also tends to increase. You could say they both decrease at the same time and they both increase at the same time, because that's the same thing on a continuum, right? An R value that's really close to 0 indicates that there is no relationship between the variables, which means that as one of the variables increases, the other one just like it's not affected at all. It's totally, completely random. It's not related. They don't tend to go together in any specific way. The best kind of graph to illustrate correlational effects are scatter plots, okay? And so each single dot represents one participant's score on both of the variables of interest. So you get an X number and a Y number because you have an X variable and a Y variable you're interested in correlating. And a single point represents a single participant's score on both of those things. So you get an X and a Y coordinate. Now, you can see in this upper left panel, this is correlation R equals 0. That means those two variables, whatever they would be, are totally unrelated, because as one increases, the other one is all over the place. It doesn't, there's no rhyme or reason to these. But you can see like a correlation, let's see in the top right panel, of positive 0.5. It's starting to look like things move kind of from the bottom left to the top right of that graph. Okay, and that means that, well, if you have high values of the x-axis, high values of the x variable, whatever that is, you also tend to have higher values on the y-axis. That's why it moves kind of in this slope or line up to the top right. Now, if you have a correlation like minus 0.99, which is the bottom right panel, that is almost the strongest negative relationship possible. And you can really easily see that because the dots tend to move from the upper left to the bottom right. As the x variable increases, meaning going further to the right on the x-axis, what happens to the y variable, the y-axis? The dots come lower and lower and lower. So as something is increasing, as one variable increases, the other one decreases. Same thing if you look at really high dots on the y-axis, that means they're going to have really low values on the x-axis, and that's why it goes from the top left to the bottom right. So hopefully that makes sense. And like I said, that negative 0.99, that's a really strong relationship, negative relationship, and you can almost imagine a single line cutting through a lot of those, which we'll talk about more in a second. So the scatter plots we just looked at would have used two ratio continuous variables because they can be scattered throughout the entirety of the scatter plot. But you might just have interval. One of the variables might be an interval variable like this. On the x-axis, you have exciting activities with partner, and there are only 5 possible values: 1, 2, 3, 4, and 5. There's nothing in between that, and so you get this kind of strange pattern where the y variable seems to be more like continuous, maybe a ratio variable, marital satisfaction. Who knows what that's measured on? But you can see that there's not just dots all over the place. Dots can only be aligned on the x-axis, at least, where there are possible values. So this is just a different look at something that still you can look at as a correlation. And it looks like there's a kind of a moderate positive relationship correlation here, where the more exciting activities you do with a partner tends to also be related to higher marital satisfaction, because you can imagine a line cutting through all of these dots that kind of looks like it starts maybe towards the bottom left, maybe around like 15 or 20 on marital satisfaction, and then moves up to the right, maybe reaching around like 35 or 40 on marital satisfaction. So that's just another type of graph you might see sometimes. So let's get into some actual hypothesis testing here. So for some of our previous hypothesis testing, we mostly talked about means, comparing the mean of a sample to the mean of a population. You could also think about comparing the mean of two different groups against each other. But in correlations, we're not comparing means, we're actually just looking for a linear relationship between two different variables. So our alternative hypothesis is just going to be that there is a relationship if you're doing a two-tailed non-directional hypothesis, or you could say there's a positive relationship, or you could say there's a negative relationship between the two variables if you felt confident in a one-tailed or directional hypothesis. For the null is, generally speaking, just that there is no relationship. In other words, the R, the actual test statistic, Pearson's R, equals 0, which means there would be no linear relationship between the two variables. So the statistic that we're going to calculate for hypothesis testing and correlations is called a Pearson's product moment correlation coefficient. Oh boy, that's a lot of words, all right? Really, we just call them correlation coefficients. If you're talking about correlation coefficient, or even you could shorten it to just a correlation of a population, then you're going to use a parameter, right? Populations and parameters go together, and it's going to be the lowercase Greek letter rho, R-H-O, rho. It looks like a P. It looks almost identical to a lowercase p, but it's called rho. If you're talking about a sample, then it's going to be a statistic, right? And then we have the lowercase letter r. And that's mostly how you see it. Now, hypotheses, whenever we generate hypotheses, we use rho because we're interested in talking about populations. But in practice, when we actually gather sample data, we calculate r. Okay, so let's take the example of hours of study and exam scores. So this is our alternative hypothesis, all right? In the population of students, there is a positive relationship between the number of hours that students study for an exam and the score on that exam. All right, what are our two variables? Well, we've got number of hours studied and we've got exam scores. Well, what kind of scale of measurements are those? Oh, okay. Well, numbers of hours studied, that's ratio. And exam score, well, that's also ratio. Okay, so can we do a linear correlation between two numeric variables? Yeah, that's exactly when we want to be doing that. So we can do a correlation here. And specifically, we're interested in if there's a positive relationship. Well, what does that mean? Well, positive relationship means as one thing increases, so does the other. So as number of hours study increases, we would also expect that those students tend to get a higher score on the exam. There might be one or two or a small handful of students that study a lot and still don't do well, but on the whole, we should see a trend, a linear trend, such that more studying tends to result in higher exam scores. So our in the kind of language of math, we're looking at an alternative hypothesis that says the correlation coefficient rho should be greater than 0. Our null hypothesis, though, is that there's no relationship between number of hours that students study and their score on the exam. So the correlation coefficient rho would equal 0. There's no linear relationship. Okay. So for step 2, we set our decision criterion, and we're always going to use an alpha level of 0.05. And remember, if we look up in a table and find that the probability of observing a particular statistic, in our case, it's a correlation coefficient is the statistic. If the probability of finding a correlation coefficient as large as we see or as small as we see, if that is very unlikely, given that the null is true. If it's very unlikely, meaning the probability, the p-value of that statistic will be less than 0.05, then we can reject the null, because that's saying that the probability of finding such an extreme correlation coefficient is very unlikely, because the p-value is less than 0.05. So it's less than 5% chance that we would see that if in fact the null was true. So then we can, any p-value under 0.05 lets us reject the null. P-value above 0.05, we fail to reject the null. All right, step 3, we collect our sample data. And it looks like we're going to have 5 total participants, 5 subjects. And we can see the different number of hours that each of those students studied, as well as their final exam score. And our job is next going to be to calculate a Pearson's product moment correlation coefficient, which just means we're going to calculate a correlation coefficient. And then we will compare that correlation coefficient to some cutoff value, and it'll tell us whether it's going to be significant or not. And that tells us whether the relationship between the two variables that we're looking at, number of hours studied and final exam score, is significant or not. And it'll also tell us, the correlation coefficient will tell us in which direction do these things tend to go together. Are they positive related? Are they negatively related? Or are they sort of unrelated? Okay, now do not freak out when you see this slide. So in order to calculate a correlation coefficient, the R, if we're talking about samples, or rho, if we're talking about populations, There are actually multiple different formulas to calculate that, and they all end up with the exact same answer. So you can use any of these that you prefer. We're going to walk through the first example using the equation correlation coefficient R equals the covariance between the two variables x and y divided by the product of the standard deviations of x and y. So we're gonna work through an example, our example, using that top equation. But again, you could use any of these equations and they would still produce the same thing. You don't have to use all of them. You can just pick one and use it. I basically never use the one on the bottom. That's a little too intense for my tastes. All right, so we're gonna ultimately calculate Pearson's R correlation coefficient, which is, again, covariance of both of the variables divided by the product of the standard deviation of both of those variables. In order to find that numerator piece, the covariance, we're going to start with this equation on the bottom, the covariance of x and y. And it's not too bad. We've seen stuff that's pretty similar to this. This is the addition, right? Sigma is addition of the products of the deviation scores of all of the x variable scores and all of the y variable scores. So we've done the deviation scores before. You've seen that multiple times by now. You've done that in standard deviation. We've also seen that in the z formula calculation. So you take all of the x scores for whatever variable x is, and you subtract the mean from all of those individual people's scores. You do the same thing for the other variable, the y variable, and then you're going to multiply all those deviation scores for each individual person. So like the first person's deviation score on x times the first person's deviation score on y. And then eventually you'll add up all of those multiplied deviation scores and divide it by n minus 1. Now conceptually, what is covariance? Covariance. This is basically how the two variables kind of tend to go together. And so you can imagine if a lot of scores for participants that are below the mean on the x variable also end up below the mean on the y variable, well, that's going to give you a lot of negative numbers that when multiplied together will actually form a positive product of x and y. And if you have high numbers on x and also high numbers on y, the y variable, then you also get very large positive numbers in that numerator, and that's going to give you a high overall covariance. So if people, let's say, taking studying a lot and getting a high grade on an exam, if those things go together, then low amounts of studying, the x variable, will go with low amounts of or low scores on the exam, which is the y variable, whereas high numbers of hours studied should correspond with high grade exams, or exam grades rather. And that should result in a very high number for covariance. If you had one of the variables when it's very high, the other variable is very low, you end up with a very low number for covariance. And if you end up with basically when one variable is high and the other variable is sort of all over the place, then you end up with a covariance of near zero. And you might think, well, why don't we just use covariance as the measure of how related two variables are, which is totally fair, right? Like it is a measurement of how these two variables are related. But we basically need to standardize how the scales of how those two things are related, just like when we saw what we were doing with z-score transformations. We want to standardize the two variables because they might be very different in terms of their variability and their standard deviation, and that could basically give us very different amounts of covariance between the two variables. And so we want to kind of standardize everything, and the way we do that is by taking the covariance and dividing it by the product of standard deviations from both x and y, and that finally results in our correlation coefficient R. Okay, the first thing that we're going to have to do is, of course, calculate the mean for each of these variables, because we need to find deviation scores for each of the variables for all of our participants. So the first thing is we find the mean. We just add up the number of hours studied, divide by the number of people, so that's 5. Same thing for the final exam score, and we get an average amount of hours studied of 3.6 hours and an average exam score of 81.2. So what I've done here is I've entered these different variables into Excel, and basically I've added new columns, okay? So you can see that for hours studied, to the right of that is the deviation of X, deviation of all of those raw scores of hours studied from the mean, the average hours of study, which we calculated on the last slide to be 3.6. So basically you take each of those hours studied for the raw scores for each individual, you subtract the mean from it, and there you go, you get the deviation of X column. Do the same thing for exam score. You take every individual's raw score on their exam, and then you subtract the average exam score from each of those, and you end up with a column for the deviation of Y. But that's not all we need to do. We don't just need to find all the deviation scores. We need to multiply those deviation scores. You can see that in the covariance equation, x minus x bar times y minus y bar. That is going to be called the deviation product of for each individual. You take their hours of study minus the mean and their exam score minus the mean exam score, and now you multiply those two things. So for instance, for participant 1, they have a deviation of X score of 2.4 and a deviation of Y of 14.8. So you multiply 2.4 and 14.8 and you get the deviation product just for that one person, which is 35.52. And you do that for each individual person. So you're multiplying the deviation from their hours of study times their deviation from the exam grade. And then you can see in the covariance equation, what do we need to do after that? Well, in that numerator of the covariance equation, we have to then add all of the products for each of the deviation scores for each participant. So you just add all those deviation products up and you get a total of 76.4. That's the sum of products. That's the whole numerator. And then we're going to divide by n minus 1 from that equation, right? We're going to divide by n minus 1. N, in this case, is 5. There are 5 participants. 5 minus 1 is 4. So we're going to divide that sum of products numerator by 4. 76.4 divided by 4 equals 19.1. That is our covariance. Now that's not the correlation coefficient yet, so we're close, but we're not quite there yet. All right, so you can see over here on the top right, the equation for the correlation coefficient, R, is the covariance over the product of the standard deviations for X and Y. So we still need to find the standard deviation for X and Y. Now you have leveled up, okay? After taking the first exam, you have leveled up and you no longer have to calculate the standard deviation by hand. You can just type that into Excel and it'll give you the standard deviation for a group of numbers, or you could use Google or whatever to find a calculator for standard deviation, as long as you input all of the individual raw scores, all right? So we can just find the standard deviation for hours studied, which is the standard deviation for participant 1 through 5. 6, 1, 5, 3, 3 are the numbers of hours studied. And if you do that in Excel or wherever you want, you find a standard deviation of 1.95 hours. That's the average distance away from the mean that each of the points are. Well, it's conceptually like that. Obviously, we know we can't actually find the average distance. For exam scores, the standard deviation is 10.55. Okay, So what we need to then do is take the covariance we already found, 19.1, and we divide it by the product of 1.95 and 10.55. And that ultimately gives us the correlation coefficient of positive 0.93. Now, this is an exceptionally strong positive correlation, meaning that as hours of study go up, exam scores also tend to go up in a very similar fashion. Okay, so there's a very high relationship, positive relationship between these two variables. And you know that because the upper end of all the possible values of an R score can take is positive 1, is 1.00. And this is 0.93. So this is a very, very, very large correlation coefficient that suggests that yes, hours studied and exam score are very related, and in what direction they're positively related. So a lot of hours studied is going to tend to go with high exam scores. Low hours studied is going to tend to go with low exam scores. Okay, here's a good question based on the data we just analyzed and the method we would have used to collect that data. Okay, so more hours of studying causes higher exam grades. Is that true? Is that false? Or can we not know from the data? The correct answer is C. We can't actually know from the data that we collected whether more hours of studying causes higher exam grades, because this is correlational research, right? We just collected information from people. How many hours did they study and what was their exam grade? If you wanted to find if more hours of studying causes a higher exam grade, you'd have to actually conduct an experimental study, which would basically randomly assign different people, different participants, to either studying more or not studying at all, or maybe studying a very little amount. And then you would see, after they had studied those various amounts, what are the resulting exam grades on average, and you can compare between those different categories of people, those different conditions. Here, we're just asking people how long did they study and what was their grade. And so we can't actually say for certain what is the causal inference here. What is happening between the two variables? We just have kind of an idea about the natural relationship between those two variables. Hopefully that makes sense. All right, everybody. Have a great day. See you in the next video.